All right, welcome to my video here. In this video or portion video, I want to discuss a three-phase Y-connected balanced motor. So the nice thing, we know a motor is a balanced load, and we know a motor is a lagging load. Because of the inductance within the motor causing current to lag voltage, a motor is a lagging voltage. Now, in each phase of a motor, there's a resistive component and an inductive component, but the impedance in each phase is going to be equal. All right, so when we connect up this motor to line 1, line 2, line 3, each phase of the motor sees the same voltage, each phase of the motor has the same impedance, and each phase of the motor has the same power factor. So that's great, because to us that means that is a balanced load, which means that our neutral conductor, if we even have one, which we probably don't for a motor, would carry no current. There is no unbalanced load on this motor. So we need a number for our example. So let's say that this is a power factor of 0.866, which gives us a phase angle of 30-degree lag. So this motor has a 30-degree lagging power factor. So I want to talk about what that means. So I've already got my phasor diagram over here with my phase voltages and my line voltages all plotted out. Now when we're dealing with current in the Y circuit, we always want to kind of talk about, well, I know my line current here is equal to my phase current. There's only that one path for current to flow. But when I'm doing calculations, if I'm going, I equals E over Z, if I'm solving for current and I'm going V over impedance, it's always the phase voltage and the phase impedance, right? So it's V of the phase and Z of the phase. And it gives me current of the phase, which in a Y circuit, we know phase current and line current are the same. But based off of that, that means that all of my phasors for current are going to be phasors. They're going to be about the phase based off of that phase voltage. So talking about line A or phase A, so let's pretend this one here is phase A. My current flowing through it is going to be lagging the voltage across it by 30 degrees. So if my voltage is here at 0, right, which maybe I'll punch the, wow, you guys know, our voltage of A to N is at 0 degrees. At 0 degrees, we know that our current is lagging that by 30 degrees. So let's put that current is actually going to be down here, IA, lagging by 30 degrees, which is going to put it at 330 degrees. Now let's talk about phase B. We see the same relationship in phase B. We're going to take the voltage of phase B divided by the impedance of phase B, and it's going to give us our current, and that current is going to be lagging by 30 degrees. So if our B phase voltage is here, which we know it's at 240 degrees, then that would put our current lagging that by 30. So our current would be here. IB will be at 210 degrees. All right? That takes us to the last one, which is phase C. Now the voltage for phase C is up here at 120 degrees. Our current is lagging that voltage by 30 degrees. So we go 120 minus 30 gives us 90. So that means our IC is going to be here at 90 degrees. Kind of like that. So that's kind of what you'd see as our phase relationships between phase voltage and phase current. And then we can also see on this phasor diagram our line voltages. So I hope that helps. Thank you so much for watching this video.